All right, let's dive right into this explainer. Picture the absolute blinding burst of a camera flash. Have you ever actually wondered how such a tiny device can release so much intense energy in just a fraction of a second? Well, that massive bright flash is made possible by a genuinely fascinating little component called a capacitor. Today, we're going to unpack exactly how these components work, the math that governs them, and why our modern world absolutely relies on them.
We've got a great roadmap for all you physics students today. We'll quickly run through what a capacitor is, the math of capacitance, the different types you'll encounter, how they act in series and parallel circuits, and finally, their real-world applications.
So, kicking things off with Section 1, what exactly is a capacitor?
Now, a really crucial thing to understand right out of the gate is that a capacitor is not a battery. Batteries create electrons through chemical reactions, right? But a capacitor, it's basically an electrical energy bucket. It consists of two conducting plates separated by an insulating material, which we call a dielectric. Because that insulating layer totally blocks the flow of electricity, the capacitor's entire job becomes storing up electric charge and energy in the electric field between those plates, just holding onto it until the circuit needs a sudden burst.
The way this actually works in practice is super elegant. When you hook this device up to a voltage source, like a standard battery, electrons start migrating from one plate to the other. This movement causes opposite charges to build up. You get one plate becoming positively charged and the other negatively charged. And because you have these opposing charges facing each other, a strong electric field forms right across that dielectric, locking that electrical energy securely in place.
All right, moving right along to Section 2, the math of capacitance. Let's figure out exactly how big our electrical energy bucket actually is.
We measure this storage ability using a property appropriately named capacitance, represented by the letter C. It's basically a simple ratio. Capacitance is just the charge, Q, divided by the potential difference, or voltage, V. So, in plain terms, this formula is just telling us exactly how much charge can be crammed onto those plates for every single volt you push across them.
And what's really cool is that we can physically tinker with our bucket's capacity just by changing how it's built. The formula here is C equals epsilon times A divided by D. So think about it. If you increase the plate area, A, you get more capacitance. If you increase the gap, or distance, D, between the plates, the capacitance actually drops. And finally, if you swap out the dielectric material for one with a higher permittivity, that's the epsilon symbol, your capacitance goes up again.
For your exams, you absolutely must remember that the standard SI unit of capacitance is the farad, with a capital F. You get exactly 1 farad if your capacitor stores 1 coulomb of charge with 1 volt applied. But here's a fun fact. 1 farad is actually a ridiculously massive amount of storage. It's so big that in everyday electronics, we almost always use tiny fractions of it, like millifarads, microfarads, nanofarads, or even picofarads.
Okay, let's step away from the math for a second and jump into Section 3, types of capacitors, to see what these actually look like in the real world. These things are usually named after the dielectric material inside them. Ceramic capacitors, they're tiny, super cheap, and you'll find them absolutely everywhere. Mica capacitors are incredibly stable, making them perfect for radio frequency stuff. Film capacitors are your go-to for precise timing and audio, while older vintage gear often relies on paper capacitors. Variable capacitors are neat because you can physically adjust them on the fly. That's actually how old-school radio tuning works. But you've got to pay special attention to the electrolytic capacitor. They pack a massive capacitance for power supplies, but they are polarized. That means if you wire the positive and negative ends backward, it will literally pop and fail.
Which leads us perfectly into Section 4, series and parallel circuits. This is a vital concept for FSC and MDCAT students. So you can wire capacitors together in 2 main ways, and the golden rule to memorize is that series and parallel combinations are basically exact opposites of each other. In a series circuit, where they are wired end-to-end, the charge is identical across every capacitor, but the total voltage gets divided up among them. But in a parallel circuit, where all the positive plates connect together and all the negative plates connect together, it flips. The voltage stays exactly the same everywhere, but the charges add up.
Let's look at how the math plays out, starting with series, which is honestly a bit counterintuitive. The formula uses fractions. 1 over C equivalent equals 1 over C1 plus 1 over C2. So if we take two 2 farad capacitors and put them in series, we calculate 1/2 plus 1/2, which gives us 1. Our total equivalent capacitance is just 1 farad. Adding capacitors in series actually shrinks your total energy bucket to less than the smallest individual capacitor in the chain. Crazy, right?
On the flip side, parallel math is an absolute breeze. The formula is just straightforward addition. C equivalent equals C1 plus C2. So if we take those same two 2-farad capacitors and wire them in parallel, we just do 2 plus 2. By doing this, we're effectively combining their plate areas, creating a massive 4-farad energy bucket. The total capacitance goes right up.
Honestly, this right here is basically your ultimate cheat sheet for the exams. Just remember the contrast. Series keeps charge the same, divides voltage, lowers capacitance, and is used to boost the voltage rating of a circuit. Parallel divides charge, keeps voltage the same, increases capacitance, and is what you use when you just need more total energy storage.
Okay, let's step out of the textbook and into Section 5, Real-World Applications.
The reality is, these things are hidden inside nearly every gadget you own. We talked about the intense, rapid energy release in camera flashes, but they also smooth out the power filtering in your smartphone and laptop so they don't crash. They're heavily used in radio and TV tuning, managing precise electronic timing, and they even deliver the massive initial kick of energy needed to start up heavy electric motors. They really are the unsung heroes holding modern electronics together.
All right, let's bring it all home in our summary section to make sure you're totally prepped for those exams.
Here is your rapid-fire recap. A capacitor is an electrical energy bucket that stores charge in an electric field. Capacitance is just charge over voltage, and it's measured in farads. When you're building circuits, remember that wiring them in series shrinks your total capacitance and divides the voltage, whereas parallel wiring grows your capacitance and divides the charge.
Now, we know capacitors dump energy instantly, while batteries trickle it out slowly. But material science is advancing fast, and engineers are constantly pushing how much energy these tiny components can store.
So, I'll leave you with this to ponder. What happens to our phones, electric cars, and even our power grids when someone finally invents a supercapacitor that holds power as efficiently as a modern battery, but charges in seconds? It would literally change the entire world. Thanks so much for tuning into this explainer. Don't forget to like, share, and subscribe for more physics breakdowns, and as always, keep learning.